Hi everybody, welcome to the Chapter 1 Intro to Physics video notes. In this section, we're going to be going through the basic system for, basic system of units, I should say, that we're going to be using in physics. We're going to be talking about dimensional analysis. We're going to be talking about sig figs a little bit, doing some examples, and finish up with some round-off error, and that'll be it for this section, okay? The MKS system, there's a number of systems that you can use in physics that are the base, you might say, units. Our system is called the MKS system, and that stands for meters, a measure of length, okay? Kilograms, a measure of mass, and seconds, a measure of time. All right, so length, mass, and time, all of these values can be put together to create most of the equations that we're going to deal with in this class. All right, so all the derived units and values we're going to get are going to come from these three base values: length, mass, and time. All right, so we have a couple of values right here that are based on either length, mass, or time. Distance, and by the way, I should probably indicate that distance is, we're going to mention this later as well, but let me make this blue here. Distance is going to be indicated by an x, right? Or at least initially it will. You might say the x direction or the horizontal direction, some distance that you move horizontally. We tend to live in a horizontal world, and so that x direction seems most like distance to us. Area, volume, velocity, all these are distance, area, volume, and velocity, acceleration, energy, are all multiples of this MKS system. They all have certain dimensions. Now you might notice that these aren't specific dimensions, but just general dimensions. For example, distance is just L for length. That laser pointer is pretty big. I'll make it smaller there. L for length, all right? Area, you know, is length times width, all right? So that is length times length, or length by length, so we've got length squared. Volume, like a cube, okay? So there's our cube. We've got length times width times height, or whatever you want to call them. So there's your L3 right there. Velocity. Velocity is very similar to speed, and if you're familiar with any kind of units you might be familiar with regards to speed, it might be something like miles per hour, right? Your speedometer in your car is a speed or kind of a velocity. So that is a length over a time. You go some certain distance in a certain amount of time. Acceleration we'll define a little more closely later on. You may not be as familiar with acceleration, but acceleration is a change in velocity. So changes happen over time. So it's really meters, or let's say, I'm going to erase that right there. Instead of meters per second, we'll go to miles per hour again. It might be miles per hour. You can think of it like that. You know, every hour you might increase or change your original velocity. That really comes down to miles per hour squared. That's an H right there, which is why we have a distance per time squared. And finally, energy. Energy is a mass times a length squared times a time squared as well. That'll have a little more, might say, concise unit later on. But all these values right here can be broken down into either L's, T's, or M's for length, time, or mass. So one of our problems, our homework problems, and I'll give you a little freebie right here, deals with that, right? It's a problem that looks like this. Sorry about my handwriting. Let's move that up there a little bit. All right, the question is, and I'll let you figure out which question it is. The question asks, what must this P be equal to in order to make this equation dimensionally consistent? All right, what must that P? That P is an exponent right there, so we have velocity right here. It's squared, though. We've got a 2 out front. We'd call that a coefficient, right? It's just a multiplier. This A is acceleration, and this X right here, like I mentioned before, is distance. So in order for this to be dimensionally consistent, what must that P be, that exponent off the X, be? All right? So velocity. We know from our previous page, and I made that too big already, velocity is what over what? Well, from the previous slide, we said velocity is length over time. Right? But if that whole value is squared, it's really going to be length squared over time squared. all right? Well, we've got our 2 right here. That can stay in there. It's just a multiplier. It doesn't change any of the dimensions. All right, that stays out front. Now, how about acceleration? What is acceleration measured in? What units or what dimensions is acceleration measured in? Well, we said just a minute ago that it is length over time squared, right? Length per time squared, time squared. It could be miles per hour, or you're going to be familiar with meters per second, all right? Both of those are length per time squared. And so we have this x right here with some exponent on it, and we want to know what the exponent is. But it would be helpful to know what value the x is. Well, what did I say just a minute ago? What kind of quantity is plain old x? That quantity is just an L, right? It's a length. It's a distance x or distance L that you would move maybe over the surface of the earth, okay? So what kind of exponent must be up here in order for this to be dimensionally consistent? Well, look at the left-hand side. We've got an L squared here over t squared. So on the right-hand side, we've got a t squared here and an L times an L. Looks like the only exponent that would work would be if that were a 1, right? Because if we made that a 2 or more, we'd have too many L's on this side and it wouldn't balance out. So L squared and L squared over t squared. That 2 is just a multiplier, so don't worry about it. 1 has to be the final answer. And I could pretty that up a little bit, but I'm just going to box it because that's our final answer. So that's how we do dimensional analysis. It's kind of a general assessment of what kind of dimensions you expect certain values to have based on what all the other dimensions are that are in the equation. Okay? We would say this equation is now dimensionally consistent. All right. Moving on. Significant figures. I'm sure this is everybody's favorite topic right here. In this class, I'm not going to hit you too hard with significant figures, this being honors physics. Although I do expect you to know how to calculate significant figures. So it's kind of like an expectation, but I feel like for this class, it's a bit of minutia that you could probably put your brain power into understanding larger concepts. However, we are going to hit it right now, and you may even be asked some questions about it a little bit later on. So know how to calculate significant figures, but on a day-to-day basis, we're not going to be that detailed. All right? That being said, what are significant figures? Well, significant figures are, you might say, a certain amount, a measurement where you have a certain degree of certainty. All right? For example, 1.02 meters. Okay? That means you have measured 1 meter, you've measured no tenths of a meter, and you've estimated 2/100ths of a meter, or you might say 2 centimeters. Okay? So all these would be significant right here. The real question is, what digits are significant and what are not? Anything non-zero is significant. All right? 1 through 9 is always significant. You can always count on that. And sometimes zeros are significant as well, but it depends on when. For example, so that'll be, I messed that up already, 1 to 9. Anything zero or anything non-zero is significant. Zeros can be significant if they are to the right of a decimal and a non-zero digit. For example, 0.90. Here, the 0 is to the right of the decimal point, and it's to the right of a significant non-zero digit. Anything non-zero is significant. So we would say that there are 2 significant values right here. You might write that in scientific notation, 9.0 times 10 to the -1 power. That kind of makes it a little bit more clear that whatever's out in front of the exponent right here is the number of significant figures, and so you would have 2. You know that's 9, and you also know that that place is 0. If you are given that value with a 0 after the 9 and after the decimal point, that 0 is significant. Zeros are also significant if they're between 2 non-zero digits. Oops, I'm trying to write with my laser pointer here. 1,009, all right? you can think of the two non-zero digits as bookends, and that they make that significant and that significant as well. So that would be 4 significant figures. What about this? 10090. Imagine your decimal point right there. This last 0 is not significant because it's just a placeholder. This still just has 4 significant figures. Why? Well, I'm kind of writing backwards right here. But if we were to write these in scientific notation, this would be 1.009, I lost my decimal point, times 10 to the, what is it? 3rd power. Okay? This down below would be 1.009 times 10 to the 4th. All right? 4 right there. This is just a placeholder telling us that all these other digits are pushed over by a power of 10. But if we boil it down to scientific notation, they have the same number of significant figures, 4 and 4, even though this is on an order of 10 greater than that right there. We're not worrying about the exponents, we're just worrying about the coefficients out front. All right, let's do a couple more little examples right here. Keep in mind, anything non-zero is significant. Any zeros to the right of the decimal point are significant, and and to the right of other non-zero digits, and any zeros between non-zeros. All right. So how many sig figs for this one right here? Well, these two zeros are to the right of the decimal point and to the right of non-zeros. So that means they're significant as well as these guys right here. And so we would have 4 significant figures. All those are significant. All right? Same here. This 0 is to the right of the decimal point and to the right of a non-zero. So significant, significant, and significant. I said and significant, not insignificant. So that's 3. No wonder people say sig figs, because significant is kind of a clumsy word to say. All right. How about this third one here? 10080. We just did an example just like that a minute ago, right? Very similar. This last 0 is not significant. It's just a placeholder, but all these other ones are. Non-zeros are significant, as well as these zeros in between non-zeros. So that would be 4. 4 significant figures. And finally, right here, how many significant figures? Well, we've got some zeros to the right of the decimal point, but they're not to the right of any non-zero numbers. There's not like a 1 out here or anything like that. So therefore, they don't count. The only thing that counts is the 3 and the 4. All right, 2 significant figures. Again, when in doubt, you can say, all right, let's write it in scientific notation, and what would that look like? Well, that would be 3.4 times 10 to the -3rd power, right? That kind of is a little clearer. Okay, there's only 2 significant figures right there. All right, hope that makes some sense. Let's do some adding and subtracting and multiplying of sig figs, and you should know for the most part how we're going to calculate our significant figures. With multiplying and dividing by sig figs, it boils down to the final answer, and it's all the final answer is all we care about. It's equal to the least accurately known quantity. That is another way to say the least number of sig figs. All right? This one right here has 3 significant figures. This one only has 2 significant figures, sig figs. So that means your final answer has to equal 2 significant figures. All right, let's go ahead and calculate this out, see what we get. 21.2 times 8.5. Oops, 21.2 times 8.5 is, do that point right? Oh, no, it's divided by 8.5. I'm sorry. Divided by 8.5. All right, so my calculator turns out this. 2.49 and then a whole bunch of 411, etc. Okay? But the final answer only has 2 significant figures, so you might just say, oh, it's 2.4, but remember the last digit is kind of rounded up, so that would actually round up to 2.5, especially since that guy right there is a 9. That would definitely round up, so 2.5 would be our final answer in significant figures. All right, so your final answer is the least number of sig figs. You might say that's the least common denominator, all right? 2 sig figs is the least amount, so that's going to be the number in your final answer. How about subtracting. This is actually a little bit easier. It's not based on the smallest number of sig figs, but it's on the smallest number of decimal places. Smallest number of decimal places in any one of the terms that you're adding together. All right, so let's take our 12.7 pounds of, raspberries, and add to it 7.25 pounds of raspberries. Let's add them all together, so that's 5,991, so 19.95. So what is the smallest number of decimal places that we've got right here? The smallest number is this one right here. There's only one decimal place. So that means our final answer equals 1 decimal. All right? Decimal. So what is this rounded to 1 decimal? Well, that would actually be 20.0. It rounds up, but only has 1 decimal place. That would be our final answer. All right, so a little bit different from multiplying and dividing, but both of them I think are pretty straightforward concepts for calculating correct sig figs. All right, the last idea right here is simply error. All this is to say that every time you do a little calculation, don't do your sig figs and don't round, because if you keep rounding, you're going to sort of compound your error down the road. All this is saying is worry about sig figs and round off your final answer. That's it. All right? Sometimes you can't avoid round off error, but for most of our problems, we should be able to. So if you do sig figs, and I do highly recommend that you try to do it on a regular basis, although I'm not going to hold you to it, just do it at the very end. It'll also save you some work as well. All right? That's our first little bit of Chapter 1 of Intro to Physics, also known as Math Review. Let me know if you have any questions. And in the meantime, thanks for watching, and I'll see you on the next one.